Good morning. Morning, Sarah. Hope everybody's doing all right. So again, make sure you are on notifications. You can get text messages for class cancellations. Hopefully we don't have any more. Fortunately, with this class, we built in enough cushion room in the beginning that if we have a cancellation here or there, we should be okay. So last week we started talking about chemical compounds, how to name stuff. What was the last thing we talked about? Because I accidentally used my Blackboard for a different class and I erased that, which is my indicator. We were going over ionics, metals and non-metals, right? We were working with metals with varying charges. Did we just started there? Okay, great. So we'll do some practice on that just to refresh, because I know that was like straight up a week ago at this point. A long time ago. All right. So yeah, we had talked about varying charges, guide to naming ionic metals with a varying charge. So what you need to do is first determine the charge of the cation from the anion. So we know the anion for sure always has a consistent charge. The cation or the metal will have an inconsistent charge. So we need to specify that in a Roman numeral, but the naming is otherwise the same. We name metal, Roman numeral, non-metal, balanced charges, and we hide the non-metal. So let me give you a couple of these. Give you a couple steps. So let's say we've got FeO2, Fe2O, CaCl2, and Ag. I want you to name all of these appropriately. Okay, so all of these are a metal. First thing is a metal combined with some sort of non-metal, which is good. Then we know it's ionic. We can follow this naming system of naming the metal and then the non-metal. So they're all ionic. Give them a little label. This is ionic, ionic. This is also ionic, and so is this. These two differ from these, though. This is what we call type 2, or they have varying charges. This is type 1. The type 1 has consistent charge. So we don't use a Roman numeral with our type 1s. So with our type 2 here, we've got iron and oxygen. So this is some sort of iron oxide. But remember, we have to put in a Roman numeral with this here. So we're going to figure out the charge of the iron. So I'm going to cut this thing in half. The whole thing has to equal 0, right? So let's figure out the charge of the nonmetal. The nonmetal is oxygen. It's 2-. Where did you get that? Find it on the periodic chart under your notes. And there's 2 of them. So it's a 2- times 2, right? Because the whole amount, my sound is messing up. Are other people having that issue? Okay. Hold on one second. Okay. Try and turn my camera off, and then let me see. I'm gonna check my booster, my internet booster. It's staticky. Are you guys still having static now? Is it better, worse? Worse, better, the same, samesies. Getting half people shaking their head, yes. It's better. It sounds better on mine, better now. Okay, let's work with that. I'll keep my camera off for now. See if I can. All right, so we got to go from this to figure out what we don't know. So we've got oxygen, which always has a 2- charge. Where is that coming from? That's coming from the periodic chart, from its positioning on the periodic chart. There's 2 of them though, so we have to take that into account. So there's an overall 4- charge happening. So if the ion or the anion is 4- in total, that means the cation needs to be a 4+. Now we have to divide it by however many we have. In this case, we only have 1 of them. So this 1 iron will kind of encompass the entire 4 charge. So this will be iron 4 oxide. The next one is also an iron oxide. So this is also iron oxide, but its charge is going to be different. So here, let's cut this in half. This whole thing equals 0. What is my anion side? Well, oxygen is always a 2-, and I only have 1 of them, so it's a 2- charge. Okay, so what does the cation side have to be? It has to have a 2+ charge, but again, we have to divide it by however many we have. So in this case, I don't have 1 iron, I have 2 irons. So I take my 2+ and I divide it by the 2. So when you're coming from here down, you multiply. When you're going from here back up, you divide. So each iron will be giving a 2 divided by 2 or a +1. This would be iron 1 oxide. You can always go back and from this, write your formula to check and make sure that you've done it correctly. These last 2, we don't need any sort of Roman numeral. Calcium always has a 2+ charge. So we're just going to call this calcium chloride. And you're done. If you put calcium 2 chloride, that's a redundant amount of information. It would be incorrect. So don't add Roman numerals when you don't need them. This one here is also considered a type 1. Even though silver is in the transition metal, we know it has a predictable charge because it's just one of the ones I told you to memorize as having a consistent charge. So this is going to be silver sulfide. E. Any questions on those? On how to classify ionics? Like, why is it ionic? Why is it type 1? Why is it type 2? Where these charges are coming from? Let me know. I've got something in here. Can we do a couple more with more division? Yeah, no problem. So let's say we have nickel 3, Ni3, N2, Cu, to S, Cr, 3P. Okay, so try all those. In each of these cases, the metal, there's more than one metal. So you'll need to adjust your total charge by dividing it. I'll give you all a minute for that. I'll give you, not a minute, I'll give you 2-3 minutes for it. Okay, so first thing, again, is to identify what it is, make sure that we're using the appropriate rules. So these first things we're bumping into are all metals, and they all have varying charges. So we would say that all of these are ionic and they're type 2. So we do need a Roman numeral. So this first one, this is nickel. Nickel has a varying charge, so I will need a Roman numeral. And then this thing is nitride. So now we've got to get that Roman numeral in there. So let's cut this thing in half. The whole thing needs to equal 0. What is the nitrogen's charge? Nitrogen always has a 3- charge, and there's 2 of them. So that's an overall 6- charge. So that means that the total charge on this side needs to be 6+. But how many are there? There's 3 of them. So I need to take my 6+ and I need to divide it by 3. Because each nickel will apply a 2+ charge, right? Nickel 1 will have a 2+, the second nickel will have a 2+, the third nickel will have a 2+. When we sum all of those things together, get out of my way, little thing, that's where the 6+ is coming from. So nickel 2 nitride would be the correct one for that. Some people, okay, Natalie, real quick, how do you determine whether there is a predictable or unpredictable charge? So you have to look at your periodic chart. Anything in the main group element, so column 1 has a +1 charge. Let me see if I'm not just talking to a random screen. So column 1 has a +1 charge. Column 2 has a +2 charge. You should have written these above those columns. Column 3, not including boron, so aluminum and really gallium, has a +3 charge. And then aluminum, zinc, and silver. Cadmium also has a predictable 2+ charge, so you could write that one in as well. All the other ones will have varying charges. So these are your predictables. This guy here, these guys here. There's something you need to make note of. Anything else will classify as a type 2, as far as the metal is concerned. Is that clear? For whoever asked that, Natalie? Okay, good. Next one here, I've got copper. Copper has an unpredictable charge. And then sulfur, which turns into sulfide. So I need to figure out the charge on copper. So I'll cut it in half. Whole thing needs to equal 0. What is the charge on sulfur always? 2-. How many of them are there? 1. So times 1. So it's just a 2- charge. So this side has to be a 2+. And how many of them are there? There's 2 of them. So we have to divide this by 2 to give us copper 1 sulfide. Just to sort of drive it home. Last one here, this is chromium. Unpredictable charge, and this is phosphorus, which turns into phosphide, right? We IDE the second guy. Cut it in half. The whole thing has to equal 0. This is, phosphorus is a 3- charge, and there's 1 of them for an overall 3- charge. What does the chromium sign have to be? 3+. And how many are there? There's 3, so we divide it by 3. So each chromium will bring a 1 to game. Any questions on that? Cecilia, is that pretty good now? Sometimes, yeah, if you just do like a bunch in a row, gets it done. Okay, so do remember, you can go the other direction. So if I give you something like this, manganese 4 phosphide. And I wanted you to instead write a formula for it. Because this is ionic and it's type 2 here, we need to balance charges. So we write the name of the metal, or rather we write the symbol of the metal. Manganese is not Mg, that's magnesium. Manganese is Mn. In this case, it has a 4+ charge. Phosphide is phosphorus with a 3-. Flip flop, we get Mn3P4. If you're given something with a predictable charge like aluminum phosphide, okay, here there's no Roman numeral to tell you the charge, and that's the important thing. That's where people always sort of get mixed up. This number is giving you the charge so that you can then find the correct formula. What happens sometimes is people will take this and just drop it down and put a 4 here. No, we've got to put it as the charge, and then from there, flip-flop charges. In this case, we've got aluminum phosphide. So aluminum always is a 3+ charge, predictable charge. Phosphide, P, phosphorus with a 3- charge. Flip-flop, it'll be 3 to 3, and we can reduce. So that becomes AlP. Okay, let's make it more complicated. Why not? We'll add some polyatomic ions in there. So keep going through here. We're good with all this, hopefully. All right. So there's we've got a compound here. It's called sodium chlorite. It's ending in ITE. You see that? It's not IDE, so it's not sodium chloride, which would be table salt. Sodium chloride. Chlorite is this thing called a polyatomic ion. Polyatomic ion. Poly meaning many, atomic meaning atom, ion meaning charged. Right? So it's multiple atoms or many atoms that are together in a packet with an overall charge. Okay. Sorry, my daughter keeps popping in. So chlorite, which is, I'll actually write this. This is the chlorite component here. It is ClO2 with a minus charge. So there's 1 chlorine, 2 oxygens, and those things as a whole have a negative charge. With your polyatomic ions, they often consist of multiple nonmetals like phosphorus, sulfur, carbon, nitrogen, and then oxygen. They usually have a negative charge of -1, -2, or -3. There is one positive polyatomic ion that you'll see, which is ammonium. Find it in a lot of cleaning products. That's NH4+. So traditionally, I would kind of have you memorize the polyatomic ions, but because of the nature of the class right now, you just want to have a polyatomic ion sheet to reference. Okay. So sulfate is a really common polyatomic ion. Nitrate also. Calcium sulfate you find in casts, CaSO4. Ammonium nitrate is a fertilizer. We've got actually 2 polyatomic ions smooshed together here. So here's a list of a bunch of polyatomic ions and organized by kind of what they have. Hydrogen, a very common polyatomic ion, OH-. This is known as hydroxide. We find that, I mean, that's the reason that like a base is a base. So the opposite of an acid or a base. Things with nitrogen in them, we've got ammonium, we've got nitrate, we've got nitrite, chlorine, we've got chlorate, chloride. One indicator that you're dealing with a polyatomic ion is the funky ending. So the fact that it's ending in ATE, now not all polyatomic ions follow this, but if you see something ending in ATE or ITE, just go ahead and reference a polyatomic ion appendix. Hydroxide, it ends in IDE, which is how we truncate and end our atoms, I know. So hydroxide, don't confuse that with hydrogen, don't confuse it with oxygen. It's hydrogen and oxygen mixed together. So these polyatomic ions, you're going to treat them just like you would treat a nonmetal, except for ammonium. Ammonium, because it has a plus charge, we would treat that as the metal. So just like you would flip-flop charges with a metal and a non-metal, when you have a polyatomic ion, you do the same thing. You flip-flop charges. They all have a charge. The charge on these things is just as important as the number of atoms for each of them. So, you don't want to just leave off the charge. Let's look at carbonate here. I'm going to zoom in on carbonate just so we can get the anatomy of a polyatomic ion really well. So CO3, 2 minus. I'm going to put a kind of a dotted line here to separate out my subscripts from my superscripts, because a lot of times people will sort of morph these numbers together or flip-flop them or confuse them. Subscripts tells us number of atoms, right? Superscript tells us charge. So we don't want to have those cross that path. So CO3 with a 2 minus charge is telling me a couple things. It's saying that I have 1 carbon. It's saying that I have 3 oxygens. And it's also saying that the entire packet of atoms has an overall 2 minus charge. Sometimes what I'll have students do is circle where the atoms are and leave the charge on the outside. So you get in the habit of treating this thing as a unit that we're not gonna like break up. The charge then applies to the entire packet. It doesn't just apply to the oxygen. It doesn't just apply to the 3, it applies to the whole thing. So now if we're trying to name something that has a or write a formula for a polyatomic ion in a metal, let's do something with carbonate. Let's do specifically calcium carbonate. So we do the same thing that we normally would. We write the metal with its charge because we're going to need to balance charges. Then we want to write out what carbonate is. Now, common faults that I see students going through every semester is they want to write just carbon. Sarah, would parentheses be appropriate like CO3 with it? No, we wouldn't put parentheses with the charge. Yeah. We use parentheses a little bit later on when we have more than one of them. But if we only have one of them with that charge, we won't use parentheses. Yeah. So something I see students doing is just writing carbon because they're not going through the process of asking themselves, is this a polyatomic ion? So ATE is identifying it as a polyatomic ion. So even we can say this is ionic, this is type 1, and it has a polyatomic ion to it. So I need to write CO3 with a 2 minus charge. I'm going to circle this so that I know that that's a unit that I want to keep together. From here now, I'm going to flip-flop. So the 2 from the calcium is going to drop to the carbonate, and the 2 from the carbonate is going to drop to the calcium. So it would be Ca2 parentheses CO3 2. Now we can reduce 2 and 2, right? So this becomes CaCO3. If you notice, I used parentheses here. I use parentheses when I have more than one polyatomic ion. When I reduce down, I got rid of my parentheses because I only have 1 carbonate. I don't use parentheses when I have only one of the polyatomics. For you, it may seem a little tricky because you may be like, oh, I want to separate this out. I want that to be a unit of a polyatomic. We can see it. Okay, teachers can see it. People who are in the chemistry field can see that that's a polyatomic ion. So we don't need to like differentiate it with parentheses. The only time we use parentheses again is if we have more than one. I'm going to do another example. Let's say we combine for aluminum and this thing called nitrate. Okay, this is ionic. It's type 1 predictable charge, and nitrate is a polyatomic ion. Again, when you start to see that ATE or ITE at the end, just reference a polyatomic ion sheet. So aluminum is Al with a 3+. Nitrate is NO3 with a minus charge. So again, I'm going to circle this without the charge, just the atom packet, so that I know that I keep that as a unit. So we're going to flip-flop charges. All right, the 3 is going to go down to the nitrate subscript. The 1 off the nitrate is going to go down to the aluminum subscript. So I should have 1 aluminum for every 3 nitrates, NO3, 3. Yes, you can have 2 3s like that next to each other. Let me show you some of the pitfalls that I have or that I see students do pretty regularly. I'll draw it in red. People will get to this point and they'll go and they'll flip-flop and they'll say, okay, 3 in 1, AlNO3. And they'll somehow sort of think, oh, this 3 is taking into account that 3. But that's not the case, actually. This 3 is involved with this oxygen. That has to be there. If it's nitrate, it has to have 3 oxygens. So we don't like this one, not properly balanced. Another thing I see students do, Al and O3, 3. And they don't use parentheses. What's faulty here? We don't have 33 oxygens. Okay. Without the parentheses, that looks like 33. So we need to put that in there. Another thing, let's see, what else do I see students do a lot? They'll do something like this, Al NO3, 3-. They'll like want to keep the charge around. Why are these two things coming together? They're coming together because there's a charge differential, a positive and a negative charge. And when they come together, they always will have a neutral charge. That's what a metal and a non-metal are doing. So the charge isn't going to stay around. You don't want the charge. No charge. Needs to be a subscript. I'm trying to think if there's anything else that I tend to see with these. Well, something pops up, we'll make note of it. So we've got a long list of polyatomic ions. You may want to, have that dog-eared in your textbook. Some of the common polyatomic ions for ATE, sulfate, phosphate, nitrate. Some of the common ITEs, sulfite, phosphite, nitrite. I'll tell you right now, 8s have 1 more oxygen than ites. So look at sulfate here. It's SO4 with a 2- charge. Sulfite is SO3 with a 2- charge. The number of sulfurs stay the same. The charge stays the same. The only thing that changes is the oxygens. So ites are always 1 oxygen less than 8s. Same thing here, phosphate. PO4 with a 3- charge. Phosphite is PO3 with a 3- charge. Now don't get the idea that ATE means 4 oxygens. That is not what it's saying, okay? It's just all the 8 is saying is it's 1 more oxygen than ite. Because look at here, what's nitrate? In the case of nitrate, we don't have 4 oxygens. We actually have 3 oxygens. But the ite still follows the rule. If nitrate has 3 oxygens, nitrite better have 2 oxygens. Okay. Charges, though, stay the same. Some rules, exceptions to the 8 in the ite idea. Cyanide ends in IDE, which you just have to know or reference. Cyanide is a capital C and a capital M. It's carbon and nitrogen. It is not, I see students do this a lot, CN-. It's not an element that we don't have with the name or the symbol CN. It's carbon with a capital N for nitrogen. Hydroxide is OH minus. Very common, we see that a lot. If we happen to add an H plus to the front of something, so like here I've got carbonate, CO3 with a 2 minus. Let's say I add a hydrogen. Hydrogen has a plus charge. Sometimes we call hydrogen just a proton. If I add a plus charge to a 2 minus charge, the charge will drop 1, right? And so instead of 2 minus, we're 1 minus. We put the hydrogen in the front. The name gets shifted. This would be carbonate. This we call it as bicarbonate or hydrogen carbonate. Same thing with sulfate, right? If I add a hydrogen, I'm going to drop the charge because there's a plus. So instead of a 2 minus, it's a 1 minus. And it goes from the name sulfate to bisulfate or hydrogen sulfate. Again, if you have a polyatomic ion sheet to reference, you don't really have to have these little rules memorized, but that's how those things relate to each other. Like if you hear, oh, it's sodium carbonate versus, oh, it's sodium bicarbonate. Those are not the same thing, okay? That they're a difference of a hydrogen. Here is a sequence. There's the chlorate and there's the chlorite. So remember, chlorate and chlorite are related by 8 having 1 more oxygen, 8 having 1 less oxygen. What if instead of dropping 1 oxygen, I actually dropped 2 oxygens? So I took my chlorate, I dropped an oxygen to become chlorite. If I drop 1 more oxygen, see this has 3 oxygens, this has 2 oxygens. What if we dropped it to 1 oxygen? I would call it hypochlorite. I would keep the ITE and I'd put hypo in front of it. Hypo is under, right? Like hypoglycemic. What if I'm at chlorate and I add an oxygen? So I'm at ClO3 minus and I wanted to have 4 oxygens. We would call that perchlorate. We'd keep the ATE ending and we'd put a per in front of it. So that's one way that we sequence out for oxyanions or for polyatomic ions with oxygen. They all have a -1 charge. It's just the oxygen number that's shifting. Okay, so writing formulas with compounds containing polyatomic ions. We kind of already talked about this, and we'll do some practice, no worries. But we want to take the metal with its charge, the polyatomic ion with its charge, and we're going to just go ahead and flip-flop. Right, so the 2 gets dropped down to the outside of the nitrate. The 1 gets dropped down to the magnesium. Again, we want to keep this as a packet. If you're dealing with nitrate, it needs to be 1 nitrogen with 3 oxygens. We can't change charges or change number of atoms. So when writing a formula, identify the cation and the polyatomic ion, balance the charges, write the formula, yada, 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 yada. So I want you to try this one. Write the formula for sodium phosphate. Yeah, Sarah, that looks good. Okay, so let's go over that one. So we said sodium phosphate. So sodium is a metal with a predictable charge of +1. Phosphate is a polyatomic ion, PO4 with a 3 minus charge. I'm going to encapsulate this thing here. Flip-flop charges. So sodium gets the 3. Phosphate just gets the 1. So I don't need to use parentheses. I can just write it like this. Oh, and let's put the 3 in there too. Yeah. Let's do as I say. All right, so 3 here, 1 there. So same rules apply as what we had before. It's just a little bit more complicated because we've got the polyatomic ion. Same thing too if you have something with a varying charge. So let's see. Yeah, so let's do these ones. So I want you to, I mean, I don't care about the 1, 2, 3. Don't worry about that. I would just look at the names. So ammonium nitrate, or aluminum nitrate, sorry, write a formula. Copper 2 nitrate, iron 3 hydroxide, and tin 4 hydroxide. I want you to write the correct formula for each of those. And know that with these ones here that have a varying charge, you treat it the same way that you would do in any other situation. Iron 3, you know you're going to be dealing with a 3+ charge. Hydroxide is a polyatomic ion. So go ahead and flip-flop and come up with some formulas. right, so all of these are, we would still classify them as ionic. There's a metal combined with some sort of non-metal. The non-metal here just happens to be a polyatomic ion, a little bit more complicated. So aluminum, Al3 plus, nitrate is, actually I'm gonna write it over here. Al3 plus nitrate is NO3 with a minus charge, flip-flop. Al, I should have 3 nitrates. So I'm gonna put the nitrate in parentheses and bring the 3 to the outside. Copper 2 nitrate, copper in this case has a 2 plus charge. That is telling me the charge, not the number of coppers. Nitrate is NO3 minus, flip-flop. I should have 1 copper for every 2 nitrates. So I put the 2 again on the outside of the parenthesis. Iron 3 hydroxide, iron is Fe with a 3 plus. In this case, again, this is telling me charge, not number of them. Hydroxide is OH with a minus charge. Flip-flop, Fe, I should end up having 3 hydroxides for every 1 iron. Last one, tin 4 hydroxide. Okay, in this case, it's Sn with a 4 plus charge. Hydroxide is OH minus. Flip-flop, I should have 4 hydroxides for every 1 tin. Sn, OH, 4. Now, if I was to write something in the reverse direction, so let's say I've got FeCO3, and I want to name this thing. Well, I need to identify what it is. So it is ionic. In this case, though, that's iron. So this is a type 2, and there's a polyatomic ion. So I list the metal first, iron. Because it's type 2, I need to have Roman numerals. And then I list the name of the polyatomic ion. And when I list the polyatomic ion, I don't change anything about it. I just say what it is. So in this case, I have carbonate. And I leave it at that. Well, I leave the carbonate at that. Now I need to figure out the charge on this thing. So we cut our metal from our nonmetal. The whole thing needs to equal 0. Carbonate has an overall charge of 2 minus. And how many carbonates are there? There's not 3 of them. There's just 1 of them, right? So 1 times 1. So 2 minus charge, which makes the iron a 2 plus. How many irons do I have? I only have 1 iron. So it will be iron 2 carbonate. Let's try another one. Let's say I've got Ni2SO4. If you get to a place where you're going to name something and you're like, oh my gosh, there's way too many atoms. This is confusing. It doesn't feel like it's matching the rules. It's a polyatomic ion 98% of the time. So reference your polyatomic ion sheet. So when looking at this, it's ionic. Nickel is unpredictable. So it's a type 2. And this clump mess over here is a polyatomic ion. So when naming it, I'm going to name the metal first, nickel. That has an unpredictable charge, so I'm going to put a Roman numeral at some point. And then this thing at the end, SO4, that's a polyatomic ion called sulfate. Now we need to figure out the charge, so let's cut the metal and the non-metal stuff in half. This whole thing needs to equal 0. Sulfate always has a 2 minus charge, and how many sulfates do I have? I don't have 4 of them, I have 1 of them. So this is an overall 2 minus charge. My metal then needs to be a 2 plus charge. How many metals do I have though? I have 2 of them, so I need to divide it by 2 for a 1. So it'd be nickel 1 sulfate. I'm going to give you a couple formulas and I want you to name them, okay? So CuPO4, Cu3P2, what do I want to do? Ca3PO4. Okay, I want you to name all of these things. All right, so you kind of get a mishmash of things in here. This first one is ionic. It's type 2 because copper is an unpredictable charge, and it has a polyatomic ion in it. So in that case, I need to name the metal first, copper. I will need to give it a charge. I'll come back to that. And then I need to name the polyatomic ion, phosphate. I don't change anything about the polyatomic ion. I just list it. Let's cut this in half. The whole thing needs to equal 0. Phosphate always carries a 3- charge. So that means copper in this case will have a 3+ charge. So this is copper 3 phosphate. This next one here is ionic. It's type 2. It doesn't have a polyatomic ion though. It's just copper with phosphorus. So here I'm going to say copper. I need a charge. And then this is phosphorus, which becomes phosphide. So often I see people see this and they automatically want to write phosphate, or they see this and they just want to write phosphide. It is so important that your ending here represent what you're talking about. ATE is the polyatomic. IDE is the element. Let's go back and fill in the charge. So if I cut this thing in half, we equal it 0. Phosphorus also has a 3- charge. And there's 2 of them, right? So this is a 6- charge. So this has to be a 6+ charge, but I need to divide it by however many I have, 3, for a total of 2. So this would be copper 2 phosphide. So when you start to mush them all together is when it gets a little bit tricky, because you're like, oh, where do I have to do where and when? So identifying is always a good place to start. This down here is ionic. This, though, is type 1, and that is a polyatomic ion. So with type 1s, or predictable charges, I don't need to put a Roman numeral. I just say what it is. So this is calcium. And then I just name whatever the polyatomic ion is. In this case, it's phosphate. See how those little details can get a little bit tricky when they all get smooshed together. So how do you get masterful at this? You practice and practice and practice. The more nomenclature, the more naming you can do, the more practice you can do, the better off you're going to get at it. We've got a couple minutes here, so I'm going to move forward. All right. Let's see. Alex, why do we not put a charge on number 3? Let me see. So why isn't this calcium 2? Alex, where is calcium located on the periodic chart? It's in column 2. What is the charge on everything in column 2 always? It's a 2+. So we don't need to put that because it's redundant information. Instead of writing this, if you were to write this, which this would be classified as incorrect. Where am I today? Phosphate. This is redundant information. We don't need that. If it is in fact calcium, calcium will always have a 2+ charge. So how do I get, you always want to write enough information to get the correct formula, but not more than you need to. So writing this, if I say calcium, calcium always has a 2+. It's just how it goes. Phosphate is PO4 with a 3-, flip-flop Ca3, PO4, 2. Was this enough information to get back to the original formula? It was. Does that make sense? Cool, awesome, great. Yeah, very, very common question where, yeah, you kind of get all the things mixed up. So if it's type 1, predictable charge, no Roman numeral. Here's a nice flow chart for naming things. Ionic, so if it's a metal, does it form 1 or more ion? If it forms 1, use the name of the element, or ammonium can also be replaced. If it's got more than 1, we use a Roman numeral. Now we're gonna do the non-metal, right? If it's any of these, you IDE it. If you use a polyatomic ion, you just name the polyatomic ion. Okay, I wanna skip through some of this. I feel like there's a lot of practice in here. I'm not against that. Nah, I guess we'll finish that up next time. All right, let's name these 2 things here. Yeah, we'll just do that. Okay, just real quick before you all head out. So this is ionic type 1 with a polyatomic ion. So all I need to do is list the name calcium. I don't need a Roman numeral for it because it's always got a 2+ charge. And then I just name the polyatomic ion. In this case, it's nitrate. Calcium nitrate, and you're done. That is enough information to get you what you need. This thing here is ionic. It's type 2, and it also has a polyatomic ion. So this is iron. We'll put a Roman numeral in there. And then this other thing is phosphate. I cut it in half. Phosphate always has a 3- charge, and there's only one of them. So this iron needs to have a 3+. So this would be iron 3 phosphate. Yeah, Lyric, this will get posted on Thursday, the Zoom meeting. Okay, good with that? Good-ish with it? Okay. So there's going to be definitely some work on your end as far as practicing. There's a good lab in your lab manual that goes over a bunch of this stuff. Okay, so we'll stop there for today. It was good seeing y'all. And then I will bump into you on Thursday. If you have any personal questions or one-on-ones, please feel free to stay around. Otherwise, enjoy the rest of your day. Bye, everybody.